Say chemistry to anybody, and probably the first thing that comes to mind is either periodic table or chemical formulae. And chemical formulae really do lie at the heart of chemistry. And your understanding of formulae is absolutely critical, absolutely vital if you're to be successful in the subject. So I've got this page from Chem Sheets. It's in their amount of substance booklet. It's basically the first page, and it has this title, Formulae. And it's quite a scary opening that they've presented. So they're saying if you can't write a formula in an instant, you should drop chemistry now and choose something else. Now, I basically agree with their sentiment. I think the message is if you don't learn to write formulae in an instant quickly, then you should consider dropping chemistry now, because I really want to get across just how fundamental, just how important it is. And if you have any aspiration of any decent grade in the subject, you really absolutely must know the formula of a substance, or at least be able to work it out pretty quickly. So we're going to start with elements, and we're just going to think about formulae of those so that hopefully they come to mind quickly. So we'll start, we've got the monatomic. So the first thing to say about monatomic is that that term itself, monatomic, means single atoms, okay? That's what monatomic means. If you look at the list, all of those are noble gases. They're all in group 0 of the periodic table. And one of the things that you know about noble gases is that they have full or complete outer shells. So if we were writing the formulae of any of these elements, they would literally be the symbol, the chemical symbol that we find on the periodic table. So helium, He, neon, Ne, argon, Ar, and so on. Okay, so if it's a noble gas, it's a monatomic. It doesn't need to be bonded with anything else because it has a complete or full outer shell, and we simply put the chemical symbol that we find on the periodic table. The next column is simple molecular. So I'm going to focus on all of them except the last two first. So you have a think, is there anything that hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine have in common? So I'll just give you a moment to think about that. Well, these are all diatomic molecules. That means every one of them comes as a pair of atoms. So we have H2, N2, O2, F2, Cl2. You get the idea. Okay, and it's absolutely vital that you remember that. If you ever have any of those substances on their own, simply as the element, and you are asked about, and you have to use a chemical formulae for them, you must remember that they come in pairs, they're diatomic. So there is a sort of a useful, I don't know if rule is the right word, but a sort of way of remembering which elements come in pairs is if their name ends in gen, or they are a halogen, so look, it's got that gen root in that, the name of that group, then they're diatomic. So we have hydrogen, we have nitrogen, we have oxygen, and then fluorine, chlorine, and bromine and iodine are all halogens. Two other elements on the list here, phosphorus and sulfur. You won't have come across this before, but in its elemental form, phosphorus exists as P4 and sulfur exists as S8, so they are still simple molecules. The A level is a little bit inconsistent in terms of enforcing this sort of knowledge, as it were. So when you come to look at melting points across period 3, which includes phosphorus and sulfur, you're very much going to have to be aware of the fact that phosphorus is a P4 molecule and sulfur is an S8 molecule. But typically when it's reaction equations, particularly with oxygen, they tend to be a little less strict about it. But it is, I think, it is important that you remember that phosphorus is P4 and sulfur is S8. We don't have to worry about ionic because there are no ionic elements, because we are just talking about the elements at the moment. And then when we come to metallic, It says here that the formula is just the symbol. So what it means is the formula of magnesium is Mg, the formula of iron is Fe, sodium Na, and nickel Ni. And so anything that's a metal, it's just simply the symbol on the periodic table. And for giant covalent, so these are these three, well, the first two, examples you learned about at GCSE. Diamond and graphite are allotropes of carbon, and so their actual formulae would both be carbon. They would both be the same because they're both just different sort of structural forms of carbon. And then silicon, which is another giant covalent, which perhaps you weren't aware of, but if you look at the periodic table, silicon is just below carbon, so it perhaps isn't that unexpected, because the whole point about periodic table is that it has patterns and trends. That's a giant covalent element, and so silicon would be just Si. So that covers the elements. So anything on the periodic table will fall into one of these categories. So now we're going to move on to compounds. So if something's a compound, that means atoms of two or more elements are chemically combined. So it is impossible, therefore, I hope you're not surprised to hear, to have a monatomic compound. Simple molecular, again, a lot of these might have, or probably did feature to some extent at GCSE. So just to remind ourselves, if there are versions of compounds that, if there is more than one version of a compound that features oxygen, so it's some form of oxide, then we differentiate between them using the name. So we've got here on the first two lists in the simple molecular column, we've got carbon dioxide and carbon monoxide. So the di part before the oxide is telling us there are two oxygens, and the mon before oxide is telling us there are one. So if we were to write the formulae of those first two compounds, carbon dioxide is CO2 and carbon monoxide is CO, and it's exactly then the same with our next two nitrogen compounds. So nitrogen monoxide is NO, it's one single oxygen, and nitrogen dioxide is NO2. Then we've got sulfur dioxide and sulfur trioxide. So the only thing that's really new there is that the tri bit in the second one, in the sulfur trioxide, that is now telling us there are three oxygens. So for sulfur dioxide it is SO2, and for sulfur trioxide it's SO3. And then the next two substances, they're pretty common in chemistry, ammonia and methane. And ammonia as a name doesn't really give us any clue as to what that substance is. So I'm afraid this is one you just have to learn. So the formula of ammonia is NH3, and I'm afraid you just have to learn the fact that that's the formula of ammonia. Hopefully you remember learning about methane when you did alkanes. So the ane bit at the end tells us it is an alkane, and they are examples of hydrocarbons, so they contain only carbon and hydrogen. And the meth part of it, the sort of prefix part of the name, tells us there is only one carbon. And we know that carbon always has four bonds, with the exception of graphite and graphene and so on. But in terms of organic chemistry, carbon always has four bonds. So our formula of methane is CH4. And then we have hydrogen sulfide, which is possibly something that we've never come across before. But if we look at where sulfur is in the periodic table, it's right below oxygen. And if we had hydrogen oxide, we'd probably pretty quickly think that must be water, which is H2O. And if sulfur is just below oxygen in the periodic table, hopefully it's not too much of a surprise to find out that hydrogen sulfide is H2S. We're going to talk about ionic compounds in a bit. We've also got here acids. I guess it's under ionic because, well, these are all strong acids, or are all examples of strong acids, which means they fully dissociate. And if you remember that for something, for it to be something to be an acid, H plus ions had to be produced. So in all of these examples, these are substances where they've dissociated so that the hydrogens have left the other part of the formula. So we have H plus ions. But it is important to know these acid formulae. So hydrochloric acid is HCl, sulfuric acid is H2SO4, nitric acid is HNO3, and then phosphoric acid is H3PO4, and they are the four most common acids, certainly the four most common strong acids, and it really will be to your benefit to learn those formulae. There are no metallic compounds, by which it means there are no compounds which have only metals in them. So just to go back to the ionic, one thing that we could have stressed is that at GCSE you probably learnt that one way of recognising that a compound was ionic was that it featured a metal and non-metal. Metallic, if you have a mixture of metals, then it is literally a mixture. There is no chemical combination, so that's how we get alloys. And then giant covalent, the only giant covalent compound that we really need to be aware of at the moment is silicon dioxide, and the name tells us the formula. So we've got silicon and dioxide, so two oxygens. Okay, so SiO2. So now we move to ions. So hopefully you remember from your GCSE how the group number that an element was in basically gave you the information you needed to determine what charge that element would have if it was an ion. So group 1 ions here, for example, which we've got on the left there, all of those will have a 1+ charge when they form ions. So we will have lithium plus, we will have sodium plus, and we will have potassium plus. Similarly, we've got group 2. So all group 2 elements form a 2+ charged ion, so that we would have Mg2+, calcium Ca2+, and barium Ba2+. And, again, aluminium's in group 3. That probably was the only group 3 element you ever used in a question. So that would be Al3+. And then it says here other common ions. So these are all substances that aren't immediately obvious by looking at the periodic table. So the first two, silver and zinc, are both in that central block, which at GCSE you would have called the transition metals. They are here. One of the things that you learned about transition metals was that they could have different charges. But that's not the case here with silver and zinc, which is why we can just present them as other common ions. So silver is always a 1+ ion, okay? It's always Ag+, and zinc is always Zn2+. And then ammonium. So ammonium is ammonia that's reacted with a H+ ion. So the formula of ammonium is NH4+. You will actually do more about ammonium later in the course. So it's important or useful to get its formulae in your head now for when you're trying to work out the formula of ammonium compounds. And then if hydrogen is an ion, you know from your reactions of acids topic that hydrogen ions are H+. Okay, they lose their single electron, have only a proton left, and they're a 1+ ion. When we look at the negative ions, we have something similar. We have something that's exactly the same in terms of if they're in a particular group. The only thing this time is that we have to just sort of count from the noble gases. So noble gases have a full outer shell, so they never form an ion. So that's our zero, as it were. And then as we go from the noble gases left, for every group that we go along, we're having to add an extra electron, to complete the shell. And for that, every extra electron it means a 1- charge or minus charge. So group 7 would be we would need one more electron to complete the shell, and so we end up with a 1- charge ion. So fluoride is F-, chloride is Cl-, bromide Br-, and iodide I-. And the one feature in the names of these ions that helps us identify them as ions is the fact that their name is slightly different from that of the element. So if we see fluoride or chloride or bromide or iodide, if we see the "ide" part in the name, then we know that we're talking about the ions. So group 6 ions are 2 groups away from the noble gases, so we need 2 electrons to complete the outer shell. So we're going to have 2 minus charges, so oxide is 2 minus and sulfide is 2 minus. And again, just to reiterate, if we've got the "ide" bit at the end of the name, we know that we're talking about an ionic compound. Then we've got this list of other common ions. So these are nearly all what we would call polyatomic ions. So that means they are ions made up of more than one atom stuck together, bonded together. Polyatomic, many atoms, right? So many atom ions. These are ones I'm afraid you're just going to have to remember. You've just got to learn them. The first 2, the nitrate and sulfate, you hope you could work out if you'd remembered your formulae of your acids that we just looked at earlier, because really for every H there would be a corresponding minus charge. So nitrate features in nitric acid. Nitric acid has 1 hydrogen. Nitrate has a 1 minus charge. Sulfate features in sulfuric acid, and that has 2 hydrogens, so sulfate has a 2 minus charge. Carbonate is a very common ion. It's going to feature a lot in your A-level one way or another. So that is CO3 2 minus. You need to learn that. Hydrogen carbonate is carbonate with a hydrogen. And if you think of a hydrogen effectively being the equivalent of a +1 charge, that means that our hydrogen carbonate is HCO3 minus. So it's like the carbonate with a hydrogen, so with a 1+ charge, so taking it from 2 minus to minus. Hydroxide is a very important ion, because that obviously is an ion of in alkalis. Hydride won't really feature probably until year 13. It's hydrogen, but the "ide" tells us it's an ion, and in this instance it's a negative ion, so it's H minus. So it's hydrogen with a complete outer shell of 2 electrons, but still only the 1 proton. And then phosphate, we can see features in phosphoric acid. And phosphoric acid has 3 hydrogens, so phosphate is PO4 3 minus. So it is so important for you to learn these formulae, to be able to bring them to mind quickly, because you're not going to be given them, and then quite often you're not given the formulae of compounds. You're just told it's barium hydroxide or it's calcium carbonate, or you're just told it reacts with sulfuric acid. So you have to learn these formulae so that you can construct the equations correctly. Because if you get the formulae wrong, it doesn't matter about balance. You can forget about balancing the equation. If the formulae are wrong, the rest of it is wrong. So I mentioned that transition metals can have more than 1 charge. That is a feature of transition metals. Technically, zinc, which we saw earlier, isn't a transition metal, but you'll learn about that in year 13. How do we know, therefore, if we've got a compound with iron in it, for example, what charge that ion would have? Well, you may recall seeing Roman numerals in formulae. So if I could have 2 compounds, for example, I could have iron 3 chloride. Okay, so that's the Roman numeral for 3 there. And I could have iron 2 chloride. They are 2 different compounds. The Roman numeral tells us the charge. So in the second example, only because I haven't given myself space, but the second example, that is telling us the charge on iron is +2. And the Roman numeral 3 in the first compound is telling us that the charge on iron there is +3. So if we were wanting to work out the formulae of these, we would have FeCl3 and we would have FeCl2. Okay, so two different compounds, one where iron has a 3+ charge in iron 3 chloride, and one where iron has a 2+ charge in iron 2 chloride. So let's just put some of that knowledge into practice just quickly. So all of these are ionic compounds. So that rule of thumb that you had at GCSE, where an ionic compound is made up of metal and non-metal, it's not 100% perfect. If you look at the third compound in this list, ammonium chloride, there are no metals present there. So some of it you just have to recognize. You will recognize really. It's a good rule of thumb. Sorry, the metal and non-metal compound. There are actually exceptions to that even. So aluminium chloride actually has covalent bonding, but it's a useful rule of thumb. You'll understand better why aluminium chloride is an exception or an example of an exception. In the case of anything else like ammonium chloride, it's about recognizing quickly that ammonium is a positively charged ion. It's a polyatomic ion, positive one. So let's just write down the formulae of the ions present first in each of these compounds. So sodium chloride, we know that sodium is a group 1 metal, and no, chloride is a group 7 non-metal. Calcium group 2. Carbonate is one of those polyatomic ions we have to know the charge and formulae of. Ammonium and chloride again. Potassium oxide. So the thing is, you're not going to be able to determine the formulae without knowing the charges and the formulae of these ions. Barium group 2, hydroxide, one of the polyatomic ions, and then it's iron 3, so we know it's Fe3 plus, and it's with oxide, so O2 minus. And then we have to have the elements in proportions such that the overall charges, that all the plus and all the minus charges cancel each other out. So we've got Na plus and Cl minus, so that's a 1-to-1 ratio. So we would have the formula NaCl. We've got calcium 2 plus and carbonate 2 minus. So that is also a 1-to-1 ratio. So our formula is just the two ion formulae stuck together. Ammonium chloride, 1 plus and 1 minus, so that again is a 1-to-1 ratio. So that's nice and simple for us. Potassium is 1 plus and oxide is 2 minus, so we need another potassium, another plus to cancel out the 2 minus. So we've got K2O. Barium is a 2 plus and hydroxide is 1 minus, so we need another hydroxide to cancel out the 2 plus charge. And now that because this is a polyatomic ion and we need to show that we've got 2 of these hydroxide ions, we actually use brackets. So that subscript 2 at the end is saying we have 2 of what's in the bracket, so we have 2 OH minus ions. And then in our we've got Fe3 plus, we've got O2 minus. We have to actually balance, we have to sort out the numbers of each of those. So it's going to be a 2-to-3 ratio of iron to oxygen for the overall charges to cancel out. So 2 ions would be a total charge of 6 plus, 3 oxides would be a total charge of 6 minus. That equals 0. That's therefore they've cancelled each other out. So it would be Fe2O3. So I've done that quite quickly. One of the things that you need to be able to do is to practice writing out formulae for a variety of compounds. But for you to even be able to do that, what you need to be able to do and be confident with are the formulae of the ions in the first place. So I hope that's been useful. If you need any help, just let me know.